Alright, so we're going to talk today about dimensions and units. I'd like to point out that the book doesn't use this word dimensions. What they actually refer to here are basic quantities. Oops. Alright, so we're going to call them dimensions. Okay, what do we mean here? If I were to ask you how tall you were, you might say something like, I'm 6 feet tall, I'm 5'8" tall. What are you really giving me? You're actually telling me the distance or the length between your feet and the top of your head. If I were to ask you the diameter of the Earth, you might say so many thousand miles. Again, what you're giving me is the length. If I laid a bunch of rulers out from the center of the Earth to the surface of the Earth. If I were to ask you how old you were, you might say so many years old. What you're really telling me is the time that's elapsed since when you were born to now. Okay, so there's some basic quantities here, or dimensions that we're using, or that we're trying to report. All right, so one of them, as we just talked about, is length. Another we just talked about is time. Right? Turns out that another is mass. And another is force. Now there's a problem here. What we'd like to have is fundamental dimensions that are not related. And everything else that can be reported or referenced back to these fundamental dimensions. And the problem is that we have a very strong relationship between mass and force. So what we have is that force equals mass times acceleration. Now, what's acceleration? I'll just do an aside here for an acceleration. Acceleration, we might report in feet per second squared, right? Well, that's really a length per time squared. So this is what we call a derived quantity, or derived dimension. So we might report something, we call it acceleration, but acceleration is not a fundamental dimension or a fundamental quantity. It turns out that we can't have both force and mass be fundamental quantities either, because they're related through this equation. So we'll talk a little bit more about what that means in a second. So here are the dimensions that we're reporting, and what are we doing to report them? We're giving a unit to go with our report, right? 6 feet, 20 years, right, etc. So those units are the things that we have all agreed on have a certain value in that dimension, right? And so that they're relative, we can understand what you mean when you say it's 6 feet tall. So there are two general agreements for units, okay? So let's talk about them. The first is the International System of Units. We call it SI. And the other is the US Customary, we call FPS, okay? So we're going to talk about length. Here we're going to have meters. Here we're going to have foot. All right? And anything else associated with length is derived. So for example, if I were to, let's put it up here in this upper corner just for a second. If I were to say, what's the area of a circle? You'd say, well, the area is pi r squared. But r might have units of feet. And so what do you report the area in? Feet squared, right? So area is a derived unit. You could also, or has derived units of feet squared. You might also say this is a derived dimension. All right? So length has different units, whether we're in SI or foot-pounds per second, and the fundamental units for each is meter and feet. Time is a little simpler. We just use seconds in both cases. But then we get to the big problem. So we got mass and force. And we have this problem with this equation right here. So what the International System of Units did is say, look, mass is fundamental, and we're going to give it a unit of kilo. What the U.S. customary system did, actually started way back in Old England, is say, no. Force is fundamental, and we're going to use units of pounds to describe force. Okay? So how do we rectify this? Well, let's talk about the International System of Units. So what they say is that 1 kilogram accelerated at 1 meter per second squared requires 1 Newton of force, right? So the fundamental unit of Newton is a Newton, and a Newton is a kilogram meter per second squared. Now in the English system they did it a little bit differently. They said, look, if you accelerate something if you apply 1 pound force to something, then you accelerate it at 1 foot per second squared. So what's the something? 1 slug. So if you accelerate 1 slug at 1 foot per second squared, you have applied a force to it of 1 pound. So here we have the units of slug. 1 slug is a pound second squared per feet. Of course, you and I would all like to be able to say what our weight is, right? So we might jump on the scale in the morning, and our scale is supposed to tell us our mass. And it reads 1 pound. And we want that 1 pound to be our mass. But we're sitting on the surface of the Earth, 32.2 feet per second squared, right? And we have a problem. When we talk about dimensional homogeneity, we need the same units on the left that we have on the right. And over here we have pounds, and over here we have pound feet per second squared. So to rectify this, we recognize that what we're talking about here is pounds force, and what we're talking about here is pounds mass. All right? So 1 pound force, 1 pound mass. So there's our relationship between pound force and pound mass. Again, 4 fundamental dimensions. Not really totally fundamental because mass and force are related. Really, the fundamental dimensions are either length, time, and mass, or length, time, and force. Depending on which of those 2 choices you make, you can either use the SI system or the FPS system. However, you can convert, just like you can convert from meters to feet, you can convert from kilograms to slugs, and you can convert from newtons to pound. Now, I'll also point out again that this is really pounds force. The book overlooks this, so this is the most important thing to get from this video, is that when we talk about pounds in the book, we're talking about pounds force.